Alright, so the solutions for the first mid-semester test. First, you have to differentiate y is equal to 3x to the 4th power times cos x sin x. Now, we have a product with 3 terms, and as we said in class, our product rule says differentiate each term one at a time. So I have what I did. I wrote back the first term and the second term and differentiate sin x and we get cos x, plus we now write back 3x to the 4th power and sin x, but we differentiate the middle term, which is cos x differentiated is negative sin x, but then we add again plus, then we differentiate the first term and we get 12x to the 3rd power, and we wrote back the other 2 terms. So that's basically our answer, and we just multiply out the brackets, or just yes, and we simplify and we get this or that. So anything you did similar to this or equivalent to this, you still get your marks. Alright, number 2, differentiate tan x divided by e to the x. I didn't see quotient rule, so I recognize at least one person who just turned this into a product rule also. But doesn't matter what you do once you get the answer. So here is the answer using quotient rule. I said I want you to put the formula less likely to make a mistake. But I don't have the formula here in the solutions. Right, but it is v squared at the bottom, and at the top we have v times the differential of u. Differentiate tan x is sec squared x minus, you write this back, and when you differentiate v, you get the same e to the x. From that, it's simply a matter of simplifying, and that's it. Number 3, differentiating y is equal to 5x plus 3 all to the 6th power. Well, if you differentiate a function of x to a power, you bring down the power there times the function of x to the n minus 1 power multiplied by the derivative of what we had called the function of x. So that is simply 30 times 5x plus 3 all to the 5th power. And that is as simple as that. Remember, these were the F region questions, so you wouldn't expect these to be to pose any significant challenge. Alright, next we have, I actually wrote we have y is equal, or we just have e to the sine 4x power. So if you have to differentiate that, what would we get? E to the function of x differentiated is e to the function of x multiplied by the derivative of the function of x. So we have e to the sine 4x multiplied by cos 4x, but this is also a function of x, so you further multiply by 4. So of course the answer is just 4 cos 4x times e to the sine 4x. And that's it. Now we go on to the D region where you are allowed to use log differentiation. So here we have it, our first question. So how do we do log differentiation? Well, when we have our question, first thing we do is we want to log both sides of the equation using the natural log ln, which is log to the base e. So we log both sides of the equation, and then we use the log rule to make the complex part of the equation a series of addition and subtraction of simple terms. So log of a divided by b is log a minus log b. I apply that rule there. Then I apply the rule log ab is equal to log a plus log b. And here, well, I don't always do this. Doesn't matter. Well, that doesn't really matter if you do this though. I apply the rule log of x to the n power is the same as n log x. And I did the same thing here. I put a 2x in front. If you don't do this rule and you put 1 over e to the 2x multiplied by e to the 2x times 2, you'll get the same answer. Same thing for this step. If you just do 1 over x minus 1 to the third power and go on from there, you will still get the same answer. But this is it is shorter to apply that rule. Good. So now that we have our equation in simple terms, now we actually differentiate both sides of the equation. So I have that, and now I want to differentiate both sides of the equation. Alright, I did one other thing. ln e is 1, since ln means log to the base e. Log to the base e of e is 1. That's why you will see the ln e just disappear, and 2x alone is left back. I didn't differentiate. ln of e is 1, so you have 2x plus 1. Good. So I basically wrote back this here, and then I put the differential operator, dx. So I'm now going to differentiate both sides of this equation. Good. So if you differentiate ln of a function of x, it is 1 over the function of x times the derivative of the function of x. That's equal to differentiate 2x, you get 2. Differentiate ln of ln x is 1 over ln x multiplied by the derivative of ln x, 1 over x, minus 3 times ln of a function of x is 1 over the function of x times the derivative of the function of x, which is just times 1. And we just simply transpose the y, and we give y the name it had initially. By definition, y was just that. So we put what y was, and that's the end of this question. Next thing to differentiate was this. Right, oh yes, a bracket is missing. Technically, no. The bracket was outside of everything on the test paper, which means the bracket didn't matter. Alright, the bracket was there because it was an adjusted question. Anyways, so first thing we do is ln both sides of the equation. So we have that. We apply log rules. I want to treat this thing as a product. So ln A times B is ln A plus ln B. Then I applied the log of x to the n power is the same as n log x. Again, you didn't have to do it like this, but this would have significantly reduced the size of the question. Next, within here, I apply the log a divided by b is log a minus log b rule. And up to here, all I did was expand the brackets. Alright, so that is that. Now, hey, at this point, you can see, well, I could have also put this x in front here and call it saying x ln e. And it will just x will remain, since ln of e would have just been 1. But I went to the option of leaving it just as it is. Once you have ln of a function with a power, you can put a power in front, or you can just leave it as it is. You still get the answer right, just with slightly different workings. Alright, so this is an example of where I left this power as it is. Good, so I rewrote this equation here, and I am now going to differentiate both sides of the equation. So now I write the differential operator ddx on both sides of the equation, and then we differentiate. So the derivative of ln of a function of x, which y is is what? 1 over the function of x times the derivative of the function of x. And you see, I kept the same rule throughout. You can take your time and look at it if you want to pause the video. And once again, all I did was kind of simplify, make the fractions look neater, and transpose for y. And that was the end of the D region. Now we go on to the C region, stationary points. Alright, now we did this very example in class. For some reason, many people still don't understand stationary points. I hope this would clear up everything for those who are still kind of lost. Alright, so we have y is equal to x to the third power minus 6x squared plus 9x plus 6. Now if we want to find the stationary points, we know by definition, stationary points occur where the derivative of y is equal to 0, where there is no rate of change of y with respect to x. So I find dy dx, which was simple enough. So I want to find the values of x that would make dy dx 0, and those values of x would be where my stationary points are. So I want to find where dy dx is 0. Now if you want to see clearly the values of x, you have to make an equation 0, which I call the roots. Maybe I shouldn't call it the roots in this case, since it will be the roots of this equation, of the derivative equation, but the only time we should reserve the name roots for the actual y function, even though it is the roots for this. We are not investigating this curve. We are investigating this curve. We are only using this to find the stationary points of this curve. This is the curve we're investigating. Good. Yes, so we find the derivative of this curve, and we see the values of x that will make the derivative of this curve 0. And the value of x that makes the derivative of this curve 0 is the stationary points of this curve. Remember, this is our subject. Alright, so let's find the stationary points of this curve. So we differentiate the curve. So good, this is the differential of this curve. Now we want to find the values of x, so we'll make this derivative 0. So we want to factorize. So I made a coefficient of x squared 1, which makes it easier to factorize. Then I factorize very simply, and I got this. Now y is 3 and 1 the answer. If we have x minus 3 multiplied by x minus 1 equal to 0, what value does x have to be to make this equation true? If x was 4, we would have 4 minus 3, 1, multiplied by 4 minus 1, 3. We have 1 times 3. X equal 4 would not make this equation 0. X equal 3 would have 3 minus 3, 0 times 3 minus 1, 2. 0 times 2 is 0. Or if x is equal to 1, we would have negative 2 times 0, which is still 0. So x equal 3 and 1 are our stationary points. Now, we know that the stationary points on a curve could be the curve's minimum or maximum value. Now, how do we know if it's a minimum value or a maximum value? Well, we use the second derivative to test. Use the second derivative to test to see if a curve is minimum or maximum. Sorry, if a stationary point is minimum or maximum. So let's test it. So let's find it, first of all, find the second derivative. And by definition, the second derivative of a function is simply the derivative of the first derivative. So we want to find the derivative of this 3x squared minus 12x. That would simply be 6x minus 12. Now we want to test to see x equal 3 and x equal 1 in this dy squared, d squared y dx squared. So what the rule says, we put in the values, the two stationary points in the second derivative, and if we have a negative value, if it produces a negative value, then that is a maximum point, and if it produces a positive value, then we have a minimum point for that x. Alright, so we put x equal 3 in the second derivative equation or expression, and we would have 6 times 3 minus 12, which is positive 6. And if we put in x equal 1, we have 6 times 1 minus 12, which is negative 6. Since we have a positive number when we put in x equal 3, then x equal 3 occurs at the minimum point. And since we had a negative number when we put in x equal 1, then x equal 1 occurs at a maximum point. Negative number, maximum point. Now, we want to find the actual values of x. No, sorry, the actual point. The actual stationary point. We know the x values for the stationary points. We know x equal 1 occurs at a maximum and x equal 3 occurs at a minimum. Right, but you want to know the actual point. Remember, this is the curve we're investigating. So you want to know what's the y value of this curve that we're investigating when x is equal to 3 and x is equal to 1. So we simply substitute x equal 3 and x equal 1 in the original expression for y, and you will see we will produce when x is equal to 3, y is equal to 6, and when x is equal to 1, y is equal to 10. Right, so our minimum point is 36 and our maximum point is 110. Now we're going on to points of inflection. Now with points of inflection, we use the second derivative to test to see or to evaluate or to find potential points of inflection. Right, so just as how stationary points is a two-step, points of inflection is also a two-step. With stationary points, we use the first derivative to find the stationary points and the second derivative to test the nature of the stationary points. With points of inflection, we use the second derivative to find potential points of inflection, and then we use the second derivative again to test to see if our potential points of inflection are indeed points of inflection. Right? So we have our second derivative. Now to check to see or to find the potential point of inflection, we want to see where the second derivative is 0. Now, what value of x would make the second derivative 0 here? Obviously, x is equal to 2. You know, you can transpose this formula also. This equation also, and just get x equal to 2, right? Just put over the 12 and divide by 6. Alright, so x equal to may be a point of inflection. Remember, the value of x that makes this thing 0, the second derivative 0, is what may be the point of inflection. So we're testing. We have to test a number just above a and just below a, and see if when we go across a point of inflection, if the signs would change. As I would say, across points of inflection, signs obtain newness. The sign must change. So we want to go just below a and just above a, and substitute those values back into the same expression. So we have the same 6x minus 12 on both sides, 6x minus 12 and 6x minus 12. But one time we have x being 2 minus a, and the next time we have x being 2 plus a. Then We just expand these brackets, so we have 12 minus 6a minus 12, and we have 12 plus 6a minus 12. So we go from negative 6a to a positive 6a. Since there's a change of sign, then x equal to is a point of inflection. And now to find the corresponding y value for the point of inflection, we put 2 in the original y equation, and we will get 8. So the point of inflection occurs at the coordinate 2, 8. Right? And that's as simple as that. So that is the end of this video. Sections F, D, and a piece of C. The next video I will hopefully finish everything.